Any questions though? Up here, how do we do with the name for this guy? I don't think we named it. I think we named the one on the left, and I don't think we named the one over here. Somebody got a name for this one? Handout. Anybody get a name for that one? Yes.
Sure. 3-chloro, 3-ethyl, 2-methyl pentane.
3-chloro, 3-ethyl, 3-ethyl,
2-methyl pentane.
Pentane. 1, 2, 3, 4, 5. 2-methyl would be that. 3-ethyl. Well, that's not right. This is not a good name because right now we have 1, 2, 3, 4, 5, 6. The longest continuous chain is now 6 with putting the ethyl at the 3. So this is really a hexane. Do what? Okay, thank you. So let's revise that. Ethyl 3-chloro. Okay, good. 3-chloro. That'd be here, yeah? Is that the structure for that name?
Yes.
Okay, 1, 2, 3, 4, 5. Okay, seems okay. Here we go. We have, basically we have 2 carbons. The front carbon has an ethyl, and a chlorine. We don't have to worry about stereochemistry really, just to give a name. In the future, maybe we would have to. That's the front carbon. The back carbon has what? 2 methyls and an H. Yeah? We can clean this up. It's basically 2 methyls on a carbon, another carbon. This carbon has 2 ethyls, and a chlorine. Carbon with 2 ethyls and a chlorine. Carbon with 2 ethyls and a chlorine, and then coming off that an isopropyl. Coming off that an isopropyl. It looks like the same compound, so it looks like it's right. Actually, there is no stereochemistry in this compound. We'll have to learn that too going forward. Neither one of these carbons are so-called chiral. So as long as you got them connected together where they should be connected, there's no projection. One at the very bottom. I don't think we did this. By the way, how many groups are equatorial in the best conformation? What was the answer for this one? 2. 1 bromine and the fluorine. You can't get both bromines. The answer ain't 3 here. Can't be 3. How about over here? What was the answer? How many groups are... let's see. This is kind of a big group. I'm going to make sure it's equatorial isopropyl. If that's there, the next chlorine is here, 1, 3. This chlorine would be also down. Those are cis, both equatorial. The other chlorine would be here. It would also be down, cis. It's actually axial. All those are cis. Could I do better than this? If I did a ring flip, right now we have 2 equatorial, right? 2 equatorial, 1 axial. If I did a ring flip, then it would be just the opposite. It would be 2 axial, 1 equatorial. these would flip. So the chlorines is a wash. So you better make sure that just this is equatorial. As drawn, that's the best one. And how many are equatorial? Again, 2, right? You can't have all 3. If this chlorine was trans, that was trans, then all 3 could be equatorial in the best conformation. But it ain't trans. It's connected cis. Any last questions about that handout? How are we doing with conformations? Unit projections and chair conformations.
These are extras.
There's another handout. Okay, sounds good, guys. Any last questions for the test on Monday? Okay, format of the test is very similar to quizzes. We'll have, what do we have? We have nomenclature. I typically have some multiple choice questions. There's plenty of those in the workbook, that type of style. And then short answers, like quizzes were, and like also in the workbook. There will be IR. That will be like in the workbook, those types of problems. We did one of those in lab last week. There could also be theory about IR. Topics, well, all the topics. What have we covered? Lewis structures, charges, formulas, DUS, hybridization, all that goes with hybridization. Physical properties, melting point, boiling point, solubility, IMFs, acid-base chemistry, yeah. Then we moved on to alkanes, conformations, some miscellaneous things with alkanes, primary, secondary, tertiary carbons, things like that, condensed formulas, etc. Question?
Can you go over acid-base extractions?
Acid-base extractions? When you're doing the extraction, you have an organic solvent and you have an aqueous. Very often it's acid or base, but it's aqueous. And the question is, are the compounds going to prefer organic or aqueous? A neutral compound will prefer organic. What type of compound is going to prefer aqueous? An ionic compound. Usually when you're doing an acid-base, really the question is, will the compound be in a neutral form or ionic form under the conditions that the extraction is being done? If it's neutral, compound is going to prefer the organic layer. If it's ionic, compound will prefer the aqueous layer. So that's the sort of the summary. Were there questions beyond that? A particular one? A particular question that you're looking at?
Oh, not really. I just want to run through.
Okay. So, any questions about the test on them? Whatever sort of the format, short answer, multiple choice, similar to quizzes. We will start at the very top of the hour. Please have pencils. Some of you are using pens for quizzes. Pencils, please. Much better. Okay, if there's no more questions, we'll move ahead to test 2 material. I'll give one handout in lab, a yellow one, 2 white ones today. The 2 handouts today. One that says Intro to Alkenes. That's for lab. You have it in your lab? You have lab today? Intro to alkenes. Looks like it got sliced off a bit there. Okay, test tube material is largely on the chemistry of alkenes. So we bring in the pi bond. Okay. Test tube will also cover stereochemistry. Stereochemistry, like enantiomers, so-called mirror images. There's a good bit there. To have an alkene, you have to have 2 carbons. Okay, you can't have a 1-carbon alkene. Simplest alkene would be ethene, that's an H. Yeah, slang name is ethylene. Ethylene. Of course, formula, 1 degree of unsaturation, right? 1 pi bond. So when you see such a simple molecule, you need to also see the structure that's there. Okay, orbitals, what type of bonds are being made, etc. But that's hopefully now this point of review. Okay, tamoxifen drug used to treat breast cancer has an alkene in the structure. Please note that the double bonds in the benzene ring, this is not considered alkenes. These are not alkene double bonds. They may be carbon-carbon double bonds, but when they're in the benzene ring, aromatic ring, they have very different properties and behavior and reactivity. There's really only 1 alkene in tamoxifen here. And we have stereochemistry though. Okay. In the end, nomenclature is covered again by video. This is the handout you need to watch the nomenclature video. Please watch. Nomenclature, you'll find it very consistent. You'll start with identifying the longest continuous chain. Okay. Some common names. Then you'll get into the cis-trans, stereochemistry. This page, very important. Not only cis-trans, but then it gets into the idea of using EZ, E or Z terminology. Okay, this is EZ. Only if you look at it, spend some time, ask questions. If you don't look at it, spend some time, ask questions. It will not be easy. It will be difficulty. Okay, please look. That's all video. The EZ terminology, we will then use the same process of determining that when we get over to things in stereochemistry. Well, this is stereochemistry, but that will be used again. And we'll say it's just like when we did EZ. Well, if you haven't did EZ, you won't be able to do the next thing we're doing. Physical properties. Maybe we can pick up there, because this is not video. A little bit of sort of review using some of the information that we've looked at during test 1. Applying it here. Here are 2 alkenes. Is this the same compound or different compounds? Well, we know these are different because the pi bond fixed the rotation and these chlorines are fixed, either cis or trans, right? Okay? 2 different compounds. They have the same exact name. They're both called 1,2-dichloroethene. They have different projections. One's called cis and one's called trans. This is trans. Okay? Just like on a ring, one's forward, one's back on a ring, if you consider the ring planar. Well, this is, if you consider this sort of the plane here, one chlorine's this way, one chlorine's that way, trans. But this is called what? That's cis. 2 different compounds. Which has the highest boiling point?
The cis one.
Somebody said cis what?
This is why? Because the electronegativity is on one end, so it's more of a dipole.
Do those dipoles cancel?
No.
No, they sum up and you get one dipole like this, right? Okay, how about these? Are these equal and opposite? Do these cancel? Yes, this is non-polar, right? That's a polar compound, polar situation. Which one has the highest boiling point? The polar one. What does polar mean? This is a partial minus N, that's a partial plus N of the molecule. Partial plus of one molecule start sticking to the partial negative of the other, and you got IMFs. And we talked about how that affects boiling point, right? Which would be most soluble in water? The polar one or the non-polar? Polar one. Okay? Which would be most stable? Why non-polar? Which is most stable? Now these cannot rotate, right? What if they could rotate? What if they could rotate? Would you rather have two groups up like this, syn or anti? Anti, right? Well, anti is sort of synonymous with trans, playing down up, where this would be sort of like cis. Which is better, cis or trans? That should hopefully be easy, because when we do Newmans, we want to make sure that the biggest groups are anti, which is synonymous with trans. There's a reason for that, because this is largely electrons. The electrons are further apart, right? This is one compound, though. This is just a rotamer or a conformer. This is two different compounds, but which one's more stable? This one, because the two big groups are further apart. Yeah? So here we are. We're applying knowledge that we hopefully got a week, 2, 3 weeks ago. We're moving on, and then we're asking the same questions in application. So this one would be predicted to be more stable. Here, the chlorines are actually pretty big. And these electrons start bumping into each other. And they're not bonding together, so they don't like each other as much. So they're like repelling, and that leads to nervousness and high energy. Right? So there's some questions we can ask. How about down here? Which one of these is most stable? Now these are not constitutional isomers. These have different names. Once you learn nomenclature, different names. Which one's most stable?
I'm saying the left one.
This one's trans. The two methyls are trans about the double bond. This one, it's cis or trans, is not applicable. It doesn't have two groups on the alkene.
But one has two sp3 carbons canceling each other out, or does that matter in the fact that the right one has an sp?
You're looking at dipoles.
No, about the hybridization of it. Does that matter?
Have you read ahead?
No.
Okay. I shouldn't read ahead.
Probably just a lucky
Never
guess.
read ahead. You got to come to class. Well, let's sort of move on to the next one. The next one's really the same question, and then we can answer it down here from the next one. Which one of these four is most stable? It turns out, now what is the relationship between these? We got to look at what are we comparing? Do they have any similarities? These are all constitutional isomers. They all have the same formula. Okay? They're all 1, 2, 3, 4, 5. They're all 6 carbons. They all have 1 degree of unsaturation. So that means they all have how many H's? 12. They're all C6H12. They're constitutional isomers. They all have different names. These are not stereoisomers. So we are looking at this. Which is most stable? Turns out the most stable is going to be this guy. The one in which the alkene has the most carbon substituents. This alkene has 4 carbon substituents. This alkene only has how many? 1 carbon substituent. The other 3 on the alkene are H's. More carbon substituents is going to make it more stable. Why? The answer down here. And I thought maybe you were referring to this type of thing down here. It's the same compounds here. It has to do with the number of the very strong type of bonds The stronger the bonds, really. Let's go through this. First of all four have one of these type, sp2, sp2. That's the sigma bond in here in the double bond. sp2, 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 sp2. Okay? All of them have one, so that's not going to give you an answer. There's two other types. This guy has four of these, sp2, sp3. All four of these carbon-carbon bonds are the same, sp2, sp3. And it's four of them. If you go across, this guy only has one of them, sp2, sp3. The other carbon-carbon bonds are all what? sp3, sp3. And it has three of those. But these are weaker bonds. Right? Weaker bonds. So this has four very strong carbon-carbon bonds. This only has one of the strong ones, and instead it has three of the weaker type. And you can see the intermediates here. In the end, take home is when you have an alkene, the more carbon substituents, more stable. Typically, if you're considering isomers, okay, we are considering isomers. Make sense? Any questions? Should be pretty straightforward. Yeah? All right, here's the kicker. In 2 weeks, I'm going to show you some alkenes and ask you which is most stable. And unfortunately, you guys will be blank. You will not remember this. Let's see. Today was Friday the 15th. Okay. Let's see. When we get over here in a couple of weeks, see if you can remember that. Now, there's lots of things you guys don't remember, but this one seems to be in particular. Try to remember this.
Review this on the 29th.
Question? Some miscellaneous things here. That is, why should we be interested in alkenes? You may be familiar with saturated fats, unsaturated fats. Which are better for you in your diet?
Unsaturated.
Unsaturated better. Saturated fats tend to want to clog your arteries. An example of a saturated fat is up top. Okay, it's got the very lipophilic side chain. They're all fatty acids. That's the fatty part, and then it has the acid, oxalic acid. That's a saturated fat. Now, you got to be careful. Okay. Now someone will say, hey, you know, saturated fats really aren't fully saturated. And you should say, yeah, I know, they have the carbonyl, which is 1 DUS, but when I say saturated, I'm referring to the side chain, okay? So that should be your response to them. The side chain is saturated. What about unsaturated? Well, this would be an example of a monounsaturated fat. It's got 1 degree of unsaturation, monounsaturated. What do we know about the melting point, boiling point of these? Saturated one is a solid at room temperature, melting point of 69. This guy, with just one double bond, the melting point went down to 4 degrees. So at room temperature, it's a liquid at room temperature. Why? Why did the boiling point go down so much? And you say because we put in a one double bond.
Well,
yes.
if we're basing it on dispersion, if they can't pack closely together like the saturated can,
yes,
then it's not going to have as strong of.
Yes, very good. It's because dispersion, things want to come together and make contact. More surface area. Why? More surface area allows more contact. But there's other things that can allow more contact. For example, these two things are very straight. Boom, lots of good contact. But what if I came in here with something like this? Well, I don't have a good example. Something that was forked. it wouldn't make good contact because it would be like forked. Only if it's linear. These guys can just stack on each other. Boom, boom, boom. IMFs, stack, 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 because it's very linear. And of course the chain can move around. Putting in this double bond, the important thing though is this cis or trans? Is that a cis or trans double bond? There's your plane. They're both on the same side. Okay. Hopefully in a day or two you need to be very quickly recognized that's a cis double bond. Really the cis really puts a kink in the chain and allows it to not be so linear and it can't stack. It's like, you know, this would be a polyunsaturated fat, more than one, poly. Okay, but basically your unsaturated fats have lower boiling points. I'm sorry, lower melting points. Now, what do you know about trans fats? Are those good? Trans are unsaturated. Trans refers to the double bond. Trans fats also bad, right? It's because if you have a trans double bond, the melting point then goes back up. Now it's a little bit counterintuitive because we also have cis double bonds in here. That one's cis. But the trans, for other reasons as well, typically the melting point would then start going back up. That is, at room temperature, they tend to going to be solid. And even in your body, although your body is warmer than room temperature, they tend to still want to be solids and clog up your arteries. Where you're unsaturated, your cis unsaturated fats tend to always be liquids and they don't want to solidify in your arteries. Okay, that's just a little application. I know there's some questions there. We could talk about it for an hour. But it's the idea of understanding cis trans and where it would be an application. There's some other things here. Identify each stereoisomer as E or Z. I have to watch the video first. Refrigerants. Heard of Freon, right? Freon is becoming outdated. There's newer refrigerants. Most of them tend to be small alkenes that have lots of fluorines on them. Or chlorine, but these are some examples of more modern day refrigerants. Okay? They give names here. And hopefully after you watch the nomenclature video, you can maybe check these names. Did they get them right, or did they make a mistake on one of them? So, you can see some compounds with the nomenclature. By the way, this one required a trans at the front. That one didn't require anything at the front. Why not? What? Okay, that's handout. Please start watching that. The other handout. Okay, we're going to, with alkenes, we will get into a good number of reactions beyond acid-base. Chemical transformations, functional group transformations. We'll convert an alkene to an alcohol. Okay? With the reactions, we have to understand things like thermodynamics, kinetics. We'll be drawing so-called reaction coordinate diagrams, which sort of describe the reaction in terms of these ideas. So that's what this handout is about. The Klein book kind of dedicates a chapter to this, like chapter 5 or 6 or so. Most books don't. It's just sort of worked in. Please use your table of contents or index for finding such topics. You cover these topics in Gen Chem, but I'll kind of present it here in the context of organic. Okay, so let's go through it. As always, we can sort of summarize and see where we're at the end. Let's go through the material. First off, consider the following two decomposition reactions. Nitrogen trifluoride will decompose into nitrogen gas and fluorine gas. Those reactions are balanced. Thank you very much. Ni3 can also decompose. There's some bond strengths given here, and then there's some questions. Which reaction gives off the most heat of the two above? What does it say on the right? Here's your chance to use your calculator. Typically in organic we don't use calculators, but here's your chance. You're dying to use your calculator.
The first one.
Which reaction is endothermic? Which reaction will occur fastest? Are the reactions driven by entropy or not? You can answer all these questions. You're good to go. Maybe we don't need to cover the handout. How are we with these types of questions? Should we cover the handout?
Yes.
Let's look at the handout. There's some other bond strengths. That's a table. I had to give you some up there because some of those are not in the table. Okay? No, you do not have to memorize every fatty unit. Okay? Obviously not. Okay. Before we get into all that. Now, by the way, those questions there are questions that you should be doing for homework. Striving to find the answers. Then I will ask you what to do. Okay, let's look at the idea of line reactions. A line reaction is where you show the reaction sort of in a line, a linear there. You've seen this before, but maybe you haven't called it a so-called line reaction. We have reactants and a reaction line or arrow, and then products. Reactants yields products. This sort of means yields. Okay? So that's one way to show it. We could show one of the reactants maybe on the reaction arrow. A lot of times maybe the smaller molecule, the reagent, where this is more the organic, the main reactant. This is more of a reagent. Put it on the arrow. That's possible. It's the same exact there. Over here on the right, we can maybe even add more information to an arrow, line reaction arrow. Here we give maybe conditions, temperature and time. So this is a very common way to just present a reaction in a line reaction format. We will also see, it's very common to have multi-steps. This is really two different reactions, but it's combined all together. This is the first reaction. That is, when you do this, ignore them. And then a week later, or whatever, then you come back and you do this. 1, 2. Very often when this is shown like this, you guys want to combine all this at the same time. It's not combined at the same time. That's the first reaction. You've got to completely do that first. Then you come in with that. This is a common way to present them. Okay. So that's the idea of line reactions. Thermodynamics. Now most of this is just a review. I'm not going to read it to you. You can read it on your own. It's in my words, but it should be a review from GenChem. Thermodynamics. This is probably a good summary down here, right? Delta G equals delta H minus T delta S. Sound familiar? At all? What is delta H? Delta H is your enthalpy. Basically heat energy. This is basically going to be our bond energies. And where do you get bond energies from? Yes, the table on the first page. Very good. Which is preferred, a positive delta H or a negative for a reaction?
Negative.
Negative delta H, which means the products have lost energy. That'd be favorable. This is also known as a what type of reaction? Exothermic. Exothermic would be a favorable reaction. Does that mean that endothermic reactions can't occur?
No.
No, they can occur too. Favorable is just sort of a generic, like it's particularly good. Okay. What is delta S? Entropy, right? Which is favored there, positive or negative?
Positive.
Positive. The products are gaining something. What are they gaining? They're gaining randomness or disorder. That's to be favorable, so positive delta S. Okay. Negative would be it lost disorder, meaning it gained order. You turn the double negative into something else. Okay, delta S, we will look at it qualitatively, that is with no numbers. Delta H, we will use our calculator. Let's do delta S first. Let's look at reaction A. Reaction A is an example where delta S is negative. Does that make sense that it would be negative? What does negative mean? I assume you can read, but if it wasn't written there, you would also know what it meant. Please make sure that you know what your terms mean, you don't get confused with the jargon, etc. Okay? I'm telling you it's negative, that means it lost disorder. What did it gain? It gained order. Does that make sense? Did it gain order? What happened in the reaction here? Two molecules became one. It's gaining order. Right? Everybody agree with that? That's why. What about the reverse reaction? B is the reverse. That's where this molecule breaks apart or decomposes into these two. Well, that's just the opposite. One molecule going to two. That's gaining disorder. It's becoming more disordered. The system has gained disorder. Delta S should thus be positive. Okay. So which is more favored, reaction A or B, in terms of entropy? B is more favored by entropy. So this is actually could be an equilibrium. And entropy would favor these two being present. Okay. What about C? Would delta S down here be positive or negative?
Positive.
What's going on here? One molecule going to one.
Yeah, but there's going to be...
Somebody said positive.
Yeah.
This oxygen is now bonding to this carbon.
But you're losing that hydrogen.
And if you look at this H is now here, because there's one, but there's two there now. It's just a cyclization reaction. It's coming together and making a ring. Delta S would be what? Is it gaining order or losing order or whatever? It's actually gaining order. Because if it's open ring, these bonds can rotate all they want. Okay? That's a lot of disorder. But once it bonds, now they can't rotate as much. So that limits the disorder of the system. The system has, what is it? Entropy is disorder.
Less disorder.
It's less disorder. So it would be, disorder is positive, be negative delta S, right?
Yes.
Yes, that's negative delta S. Do you understand how once it makes the ring? So it doesn't always have to be one molecule going to two, etc. This is one molecule going to one, but there's something else going on. the ability for all the bonds to rotate. Okay, delta H. Delta H is easy to quantify because we can use bond strengths. Look at this reaction. It's very similar to the one A above, except I think we're missing a carbon here. And this is a reaction that we will certainly cover. Reaction of an alkene with like HX, HBr, HCl, to give an alkyl bromide. The alkene is now gone. What is delta H for this reaction? By the way, real quick,
Positive.
which term does temperature magnify? Delta H or delta S?
Delta.
Okay. Back to this. Delta H. We want to look at what bonds are broken and the strength of those bonds. The pi bond is broken. It's gone. A pi bond is 63 kcal per mole. Is that what it says in the table? Because sometimes I get my numbers from different tables. Can you look at the table and find that? Does it say 63? Anybody have the extra of these handouts? Are there extra of these? Thank you. I don't think the pi bond came from here. You got to be careful. There is some pi bond compounds down here. It says 174. What this is, I know, this is the entire bonding between the two. Both the pi and the sigma bond, 174. So you got to be a little bit careful. The number, what did I give you, 60 something? That's actually just the pi bond. Now don't worry, I'm not going to confuse you with finding values. Do a little practice and then we'll see if there's any issues with finding numbers. But I got some of these numbers from a different table. What else is broken over here? The HBr bond is broken because it ain't there now. What's the bond strength of an HBr? I think that is in the table. On the right side, kind of midway,
87.
HBr, it says 87 kcal per mole. So that looks like I maybe got it from that table, or the, okay, right? What was broken? Anything else broken here? Actually, no. 150 kcal per mole broken. What was formed? We got a CBr bond formed. But we got to make sure, we have to know what type of carbon this is. This is a primary carbon. So it's a primary CBr. Is that in the table? Right side, go down. You see bromines attached to carbons. Is there an example where the bromines attached to a primary? What's the value? 72. What did I put here?
69.
Okay, I got it from a different table. The table I got it from said 69. You want to write 72 there, just okay, but that's where you would get it from this table. We also formed, if you look at it, we formed a new CH bond, and it's a primary CH. Primary CH in this table would be what? Left side top. Be the second one, 101. 101, well, it says 101. This is what's formed. The difference is 20.
Is there a reason why you didn't include the forming of the CC bond?
Of the what?
Of your single carbon-carbon bond?
It was already here.
Oh, you just maybe left
We
it?
broke the pi. The sigma bond is here.
Yeah.
It's still there.
Oh, that's what you're, that 63 is just the pi bond. is
The
that-
63 is just the pi
got it,
bond.
got
Yeah.
it.
Yeah. If it was for both, then we'd have to go back and maybe put it in over here.
Yeah.
Okay, the difference is 20. Is delta H positive 20 or negative 20?
Positive.
It's negative 20.
products minus reactants, right?
Is it positive 20 or negative 20? Is delta H positive or negative?
I think it's negative.
Negative 20.
Negative 20. Why is it negative 20? Why is it negative 20? What are you trying to think of?
It's exothermic because you're forming bonds.
Oh, good. Say it again.
Breaking bonds is endothermic, it requires energy, but exothermics releases energy, so it's plus 20.
Yeah, but why do you say this is exothermic? Can you explain why you're saying it's exothermic?
Is it because we're using bond energies? So you just go like from left to right using the bond energies?
Which side has the stronger bonds? Left or right?
Right.
Stronger bonds. These values, this is the amount of energy it takes to break the bond. It's a bond dissociation energy. It's a bond strength. Bond, okay? It takes more energy to break these bonds. These bonds are stronger. Stronger bonds are more stable. This reaction should be exothermic. You're making more stable. Stronger bonds are more stable. Stronger bonds are also lower in energy. More stable a bond, the more lower in energy it's going to be. These bonds are less stable. They're higher in energy. You've got high energy bonds, and you're making lower energy bonds. Where does the rest of the energy go? Less energy. How much energy? 20 kcal per mole. The reaction gives off that energy because the bonds are now more stable. Reaction is exothermic. So delta H is negative 20. Right? If we had to put energy in, it would have been positive 20. The system, this is now the system, has lost energy. It's negative 20. I reckon that means that it's 150 minus 170. I don't know. That's not the way I look at it. I look at it, okay, which side's stronger, then it's exothermic. There we go. It's negative 20. What about the delta S? So, is the reaction we just looked at, is it favored by enthalpy? Is it favored by enthalpy?
Yes.
Delta H. Yes, it's exothermic. But is it favored by entropy? No, 2 molecules going to 1. That's not favored by entropy. So how is it favored overall then? Why do you say it's favored overall? You have two different terms. How do they influence the overall delta G?
I'm completely confused. If you have something, if it takes 150 kilocalories per mole to form the left side, and it takes 170 kilocalories per mole to form the right side.
Oh, it doesn't take, that's how much it takes to break.
To break them, oh.
These are bond dissociation energies.
Okay.
That's how much it takes to break them. The right side is more stable. Good, you're asking questions. We'll pick up here. After the test, please look ahead. For example, do this calculation here, just like we did. The other calculations. Also be thinking about the questions on page 1. See some of you this afternoon downstairs for lab. Have a good day, guys.